So in this video I'm going to talk about the interference by thin films. So you can see on the screen, so the colors on a soap bubble are on a thick slick of oil. So this is a particular optical phenomena, and this can be explained using this model, the interference by thin films. So the colors on the soap bubbles, oil slick, etc. can be explained using this phenomena of interference by thin film. So thin film is a transparent material with small thickness of the order of wavelength of light. So maybe this thickness should be of the order of few hundred nanometers or micrometer. So if we have such a material, so this will be known as a thin film. And this thin film may be perfectly reflecting or perfectly transmitting for a particular wavelength. For example, if you have a green light, so it's a particular this thin film can act as a perfectly reflecting material, or for other wavelength it can be perfectly transmitting. So this we will discuss next. So let us talk about this schematic diagram. So here look, this is air or vacuum, and this is also air or vacuum. So here we have n is equal to 1 and n is equal to 1, and here we have a material. This is our material whose thickness is d, and remember this d is very small, and it is of the order of nanometer or micrometer. So its refractive index is greater than 1 because this is a material. It may be a glass, or it may be some oils, it may be some oil or soap bubble or anything. So thickness is very small, and a wave is incident on it. Remember this wave or light is incident at normal. So this is normal, so it is coming like this. So this is the interface between these two mediums. So this is air and this is the medium. So you know that whenever light or any wave is incident on a denser medium, so a part of it is reflected. So a part of it will be reflected from this particular point, and of course this should, if this is the interface, so it will go like this. So a part is reflected from here, so I name this part as I, or 1. This is 1 basically, while the other part will be transmitted in this medium. So again at this interface, at the boundary of this will be reflected from this boundary, while the remaining will be transmitted. So this is wave 1 and this is wave 2. So these two waves are originating from one single wave, so therefore these are phase coherent, and they will show the phenomena of interference. You should remember that the incident wave comes like this, and a part is reflected from here, while the other part travels here and it is reflected from here. Here, for the sake of convenience, I have drawn this diagram like this, while this is not the actual or true diagram. It is only for simplification. So now we have two waves, wave 1 and wave 2. So since this wave is reflected from the boundary of a denser medium, so this is a rare medium and this is a denser medium because it has more refractive index. So therefore it will suffer a phase change of pi. We know that if there is a wave and this wave comes at the boundary of a medium, and when it is reflected, if it has more refractive index than this medium, so the waves that goes reflected will suffer a phase change of pi. So there will be a phase change of pi. So ray 1 upon reflection from denser medium, so there should be a phase change of pi, and you know this phase change pi corresponds to lambda by 2, because this is one complete wave and this is from 0 to 2 pi, while this is not complete, is known as lambda. So lambda is proportional to 2 pi, and similarly if there is a phase change of pi, so this will be proportional to lambda by 2. So a phase change of pi correspond to so the phase change is pi, that correspond to lambda by 2. Similarly the second ray that travels like this and then goes back, obviously. So it covers a distance. If this is d, so it comes here and it goes where, so it cover a distance of 2d. But since this is a denser medium, so we need, if we want to find the distance traveled or the path covered, so we need to multiply by refractive index, that is n. So the optical path will be 2nd. So now what is the total path difference between these two waves? This wave have a path difference of lambda by 2, while this wave have a path difference of 2nd. So this is the total path difference, that is 2nd due to wave 2, and this is lambda by 2 due to wave 1. So this is the total path difference. So, and now this is a double slit arrangement, because there is one source and these two sources are phase coherent and they are interfering with each other. So we can use the condition for double slit. So if the path difference is m lambda, then we have the constructive interference and we will have the maximum intensity. So, and if this path difference is half integral multiple of lambda, then we will have destructive interference and we will have minimum intensity. Or we can simplify this relation. So if we can take this lambda by 2 on other side, so this gives me m lambda plus minus lambda by 2. Or we can simplify this, so this gives me this condition. So if this 2nd is equal to m plus half lambda, so there should be constructive interference. And similarly, we can shift this lambda by 2 on other side, so this lambda by 2 with this lambda by 2 will cancel out and we will have 2nt into m lambda. So if we have this condition 2nd is equal to m lambda, so there should be destructive interference. So these are basically the conditions, and the next I will solve some problems on the interference by thin films, then it will get clear. So problems are very interesting, so I will be solving these problems in next video. Thanks for watching.